Hi, I'm Charly Molter, and I'm an engineering manager at Kong. Um, the teams I'm responsible for work on the service mesh product, right? For Kong, it's contributing to the CNCF project Kuma, which is an open source service mesh. The enterprise offering that we offer on top of that is called Kong Mesh. And finally, what we call Mesh in Connect, which is the SaaS offering of our service mesh. And so I'm here today to try to explain to you and convince you that there's a bit missing in the APIOps, right? And I think this is a bit where service mesh can help a lot. And this bit is reliability. Okay, cool. So let's get started and we'll see how we can add reliability inside APIOps and that this is something that is missing at the moment. So what is APIOps, right? If APIOps was built 10 years ago, it would have been called API-driven development. Because at the core of it, what it is about is write your API spec first, right? To write your API spec first, you're probably going to use something like OpenAPI, right? OpenAPI is a specification language, which usually takes the form of a YAML, that describes your API. So it describes everything, like what endpoints, what methods, what are the payloads, what are the response codes, etc. All this is defined inside a YAML. But OpenAPI is a little bit more than that. It's an entire ecosystem. Because once you have the spec of your API, you can actually use a lot of toolings for that. So you can lint it, right, to ensure that your spec is conformant to the highest standards of building APIs inside your company or more generally in the ecosystem. You can generate code, especially client code. So nowadays, you do share your OpenAPI spec instead of sharing a library, right? What is the advantage of that? Is that you can build clients for all sorts of languages, right? The implication of that is that these are going to be thin clients, and we'll get back to that in a minute. And then you can also generate boilerplate server code to get you up to speed quicker. And we'll look at this in a minute. The other bit of OpenAPI, of APIOps is Git, right? Git, but not only Git, right? Nowadays, when we say Git, we have a tendency to think GitHub's GitLabs, right? So on top of Git, you get more stuff. You get CI, you get CD, you get automations and things like that out of that, right? So this is what APIOps is. You start by writing your spec, right? And out of that, you check it in, you get pull request reviews and things like that to actually build up your APIs from there. So you start from the definition, from the specifications, and then you build up the code and the deployment from there. Okay, so what do we commonly do nowadays when we write services, right? So we add a new service, rewrite some code, and this service is going to receive traffic from either other services inside the organization or from the outside world, right? Inside the organization, we usually call that east-west. Outside of the organization, we usually call that north-south, right? And to fulfill the request coming in, we're probably going to talk to other services, right? Same thing. These services might be inside our organization or outside altogether. This is what we commonly do when we write microservices, taking requests, do other requests to actually answer these requests coming in. Cool. So if I were to build this kind of service in an APIOps kind of way, I would start by writing my YAML, right? So you write this YAML here. Kong has a great editor called Insomnia to help you out doing that and write tests and things like that that goes with it. You can actually get a link here in the slides to the full spec that this is an extract of. So we can easily see here, there's a path, there's a parameter in this path. We define a GET request that actually returns an OK response with this schema as an API response. Okay, that's simple. So now we can use a generator to actually generate all the Go structs and things like that that I needed. We're going to use Go generate, so it's simple, and we're going to build just this simple boilerplate code to actually start that, right? 5 lines, that's all there is really. So we're going to run Go generate, right? And now to actually implement my server, all I have to do is concentrate on the business logic, right? And the great and important point about the business logic is that this is what you're paid for, right? You are not paid for building the random structs that defines your JSON payloads, right? That's not where you provide value, right? Where you provide value is writing the business value, because the business logic, because this is what you're knowledgeable about, right? So here we can see there's a home endpoint, right? There's an API dynamic endpoint. There's an API dynamic path endpoint. And then I can implement this interface, and each of these methods are going to do what they need to do, right? So we take the request in, it's probably going to call all the services to actually fulfill this request. That's simple. So now I've wrote my server. I probably wrote test. It's working, etc. I probably built a Docker container out of that. So I want to run it, right? So all this was checked into Git. My Docker container is published as part of my CI. And now I'm going to write a Kubernetes deployment, right? Because why not? That's pretty common. So I write a Kubernetes deployment. Once again, a YAML. I'm probably going to check it in this same repo. And I'm going to have CI to deploy it, right? Maybe you're going to use raw Kubernetes. Maybe you're going to use something like Argo and Helm chart to make it work. But it doesn't really matter. All that matters is that you put that into your Git. You're probably opening a pull request to actually review this. You're going to run some CI to ensure that it follows some standards, right? You see where I'm getting. So here we got the spec. We wrote the code, right? We wrote the deployment spec to actually ship the code, and that's it, right? Our app is running. Cool. But isn't it just the beginning, right? So first thing that's likely going to happen is someone's going to use your API, right? And congratulations, because someone is actually using your API. Sometimes you build something and no one uses it, which is a little unfortunate. Here, someone did it, right? So here I have someone trying to consume my API that says, actually, I'm getting 500s, right? And now you get in these more common things, right? We broke the wall between ops and devs, right? So now we actually operate what we build, which is a good thing, right? But we spend a lot of time actually trying to figure out why the thing we're trying to run doesn't run well, right? And it's the beginning of the story. So we write an API and then we got to keep going, right? We got to keep incrementing. We discover problems and we fix these problems, and we need to discover more problems, and we add new features and things like that, right? And it's a good thing, right? But in these API ops, like now there's nothing that helps you there, right? There's no more to that. But there was ops in the name, right? And I think this is what we're missing and what a service mesh can help you with, right? So what is a service mesh? So I'm going to do the impossible task of doing a 1-minute introduction to what a service mesh is. Okay, so in its most common architecture, a service mesh is going to be a proxy next to each instance of each of your servers, right? This proxy, that is most commonly Envoy, is going to intercept the entirety of the traffic coming in your instance and out of your instance. What is very important about this proxy is that this proxy is going to be dynamically configured from what we'll call the control plane. I'll get back to that in a second. By dynamically configured, I mean that you never need to restart the proxy, right? We're going to change the configuration, and the proxy is going to reload it, and then the traffic is going to get impacted. Protecting certificates, same story. Everything. Adding new services that you can connect to, all dynamic. So, as I said, the control plane is actually going to configure these proxies, right? And when we talk about a service mesh, in practice, 95% of the complications is inside the control plane. It's the brain of your service mesh. So what this control plane is going to do is, for each proxy, is going to take the state of the mesh, right? So what is the state of the mesh? It's the different services, which and where the instances of each services are, and other configurations of the mesh, right? It's going to take all that, and whenever there's a change to it, recompute the specific configuration that needs to be updated, send it down to the proxies, right? And then the proxy will have the configuration updated. So I said there were three things mostly in the state of the mesh: the services, the instances of these services, and then finally the configuration of the mesh, right? So what is the configuration of the mesh? What we usually call the configuration of the mesh is what we call policies. So what are policies? Policies, in the simplest way, is the configuration that is going to impact the traffic coming in or coming out of the traffic of the proxy, right? Kuma has a very, very powerful policy system that is heavily inspired from Gateway API. If you don't know Gateway API yet, you will get used to it because this is what's replacing ingress in Kubernetes. So if we take an example, policies roughly always look the same. They have a kind at the top, right? They have a name because everything needs a name. And then they have what they call target refs. There are target refs in three different places. There is the top-level target ref. The top-level target ref is going to define precisely which proxies are going to get impacted by this target ref, by this configuration, right? So here, if we look at the top-level target ref, we have a mesh subset and we have tags team A, right? So we're going to impact all the proxies that have the label team with the value of A, all of them, right? Inside the entirety of the mesh. And then there are other target refs, which are from or to target refs. From target refs is you're going to impact traffic that is coming from this target ref to the proxy you're identifying with the top level target ref, right? And two is the opposite, right? So it's the traffic coming out of your service, right? So in that way, you can very easily identify traffic coming from service to another service, right? So here, for example, we have a mesh timeout. And so as I said, I want these proxies with team A to actually, whenever they receive traffic coming from anywhere in the mesh, they want to apply a request timeout of 2 seconds. Okay, cool. One great thing about service mesh is observability out the box. So here's an example: Grafana dashboards that come out of the box with the stock metrics. What is great about that is that you can build default dashboards so that people that build new services get with a good baseline. And this baseline can be the same between all your services in your organization, which is very helpful because then your SREs or things like that can have reusable skill because they can develop habits of what normal things look like because they used to see the same thing, right? We're pretty good at doing pattern matching as humans. So we should build tools that leverage that. So then when we look at actual policies, the first thing we're going to do is preventing flake with retries, right? So how do we do that? We're going to use the mesh retry, right? So we take a top level target ref, which says, I want all my mesh to be impacted by this. And then we're going to do a 2 target ref. And we're only going to say, if you are actually trying to talk to API play and only the service, just a reminder, API play is the service we just wrote earlier, we're going to have a retry of 10 times with a base interval of 100 milliseconds and a max interval of 2 seconds. What is very cool here is that you've actually modified the proxy of your clients, right? And your clients will do these retry policies, right? This is equivalent, if you think about it, as having a library, having the retry code to the library, and having all your clients update to this little latest version of the library. Except now you're using APIOps, so there's no more libraries. There's just a spec, right? And there was no way to express these kind of things in the spec. Now you can do it with a service mesh. What is even greater about that is that you control who gets that, you control at which speed, and you can easily update it live, which is very important if you're firefighting an issue, right? So let's dig down and look at some more policies. So then we're going to prevent tail latency with a timeout, right? Tail latency can be a problem. Like slow is the new down. It's a common saying, right? That Marco, the CTO of Kong, has actually said a couple of times. And it's important, right? So here, we're going to set a timeout, as I showed earlier, right? So any proxy in the mesh, when they try to talk to API play, they should abort if the request is lasting more than 2 seconds. If I have an SLA, it's a good way, right? I have an SLA. I know that like things are never going to take more than 2 seconds or very rarely. So if something takes more than 2 seconds, the client should just retry, right? If you combine timeout and retry, your tail latency will go down drastically. So this is very important as well. Again, not something you can explain you can express in your API in your OpenAPI spec, right? And this is very easily done that way and controllable by you. Next thing, rate limits, right? So rate limit is the other way around, right? It's a from policy. So the proxies that we're going to impact in this target ref is this API play, right? So the proxies that implement the API play service, when they receive traffic from any other proxy in the mesh, they're going to have a rate limit of 1,000 requests in a 10-second interval, right? This is all great. What is great about all these algorithms I've showed you is that the configuration is there and the code is in Envoy, right? Envoy has seen more bytes than you'll ever probably put through a proxy yourself, right? It's used by Google. It's built by Lyft. It's been used in Twitter. It's used absolutely everywhere. And so these are strong algorithms that are going to be so much better than whatever your devs do actually write. So the next up, and one of the very strong feat of Kuma, is that we can do multi-cluster failover for disaster recovery in a very simple manner. So here, let's look at it. We're going to use a mesh load balancing strategy, right? It's a 2 policy because it's, again, something that your clients are going to want to do. So all the clients in the mesh, when they talk to API play, I want to do a locality-aware cross-zone failover. So here, let's say I have 4 regions, right? I have a US East region, a US West region, a EU East region, and an EU West region, right? And I want to do this common thing. I want to failover US East to US West and vice versa, and EU East to EU West and vice versa, right? What I never want to do is to have US traffic go to EU and EU traffic go to US, right? Either for compliance reason, because of laws and things like that, but also because the latency across the Atlantic Ocean is probably much bigger than the intercontinent latency, right? Intracontinent latency. So this is how I define that. It's very simple, right? And you can do very advanced things. You can say, I want to fail over to anywhere except this sensitive place that I don't want to send any data, and it should leave by itself. And this is very powerful because you do it on a per service basis, right? It's not the entire company that decides how to do it. Your databases that don't know how to failover, or the failover is integrated inside the database because you're using, I don't know, something like Cockroach that is very clever at doing multi-data center, can have a different policy than your other stateless services. You can do anything you want, right? You can have people roll together slowly or not at all, right? You can have only some clients failover and not all of them. Like you might want to say, only my critical clients are going to fail over because it has a cost to do that. But my non-critical clients are just going to fail if we're bad, right? And the great thing about that is that it's fully automatic, right? As the traffic inside your own zone is going to degrade, we will progressively route traffic to the remote region, right? This is going to minimize the cost of doing multi-region, but at the same time, maximize your SLO, because as things degrade in one region, you will go out and then it will come back if it heals back. Okay, cool. So here it is. We just went over a bunch of examples to show you that Kuma can bring the declarative way to define reliability properties of your service, right? So we showed that Git gives you version control, right? You can easily check in files in. You get everything that goes nowadays with Git, which is GitLab, GitHub, that actually gets you CI, pull request workflows, development workflows, team coordination, and stuff like that, right? So you get that out of Git. You get OpenAPI, which comes with its ecosystem that are going to help you build better API quicker. You're going to get testing things and all that things that goes with it, right? Through the OpenAPI. So you're going to write better code and standard code and nicer services, right? And then you're going to ship it on Kubernetes. Same thing, Kubernetes is an entire ecosystem, right? With it, you're going to be able to run your containers very easily. And then finally, the missing bit that I've introduced today, which is Kuma, a service mesh that enables you to declare the reliability properties, declare how you're going to handle the fact that things are deployed between different clusters and how they should talk to one another, right? How you should retry, how you should rate limit, and all that kind of thing. And this is why I think that with this corridor, you can actually build the greatest microservices that will achieve the highest reliability and give the highest velocity possible to your devs. Okay, cool. Thank you very much.